So this is going to be the last session for this course. We will here also we will try to solve some question and of the previous assignments, and I will give some time to solve those. Give you some time to solve those question, and afterwards I will solve it for you. Okay. So. Okay, so let me present the slide. Yeah, so my slides are visible, I think. So the process is same. So here I will provide you some question. Whatever will be the answer, you will put it in your answer will be in the chat box, and after that I will discuss those questions. Okay. So today's first question is this one. So this is a short question, so I won't give you much time. So please tell the answer. I mean, it's a informative type of question. So okay, one answer I have got. Okay, so the right answer is D, obviously. So this is a card-free catalyst, iridium-based catalyst, that is, and this is the Strock or Osborne catalyst. And this is the Wilkinson catalyst. So these all three are used for hydrogenation reaction. Okay, and one thing is that after the this is basically a dihydrate catalyst. Okay, so these three are also dihydrate catalyst. But you can see that in the chemical structure of these three catalysts, there are no hydride is present. So what is happening actually here? So as you know, maybe, so after the ligand dissociation, so first step is the oxidative addition of hydrogen. Okay, so because of that, hydrogen is attaching to the metal center, and it is actually preparing the active dihydrate catalyst. Okay, that carry forward the further reaction. Those steps are there, obviously, and this catalyst is used for hydroformylation reaction. And hydrocarboxylation reaction. Okay, so I think it's clear now. So which catalyst is for what? And one more thing also, these Wilkinson catalyst are can do hydrogenation when the olefins are either monosubstituted or disubstituted. And these two are good for any of the olefin. Okay, so either it can be mono, di, tri, even tetra. Okay, tetra substituted olefin are also possible. These catalysts are also possible. So these catalysts can do hydrogenation reaction in the olefin where mono, di, tri, tetra substitute substitute is present. And also, if you want to synthesize some stereoselective or stereoselective, the olefin, not olefin, hydrogenation after the product you want to have with stereoselective product, then these type of these two catalysts are acts very well. Okay, but for the non-selective purposes, we generally use the Wilkinson catalyst. Okay, so I think this is pretty clear now. So let's go to the next question. This is also an informative type question that give it a try, please. No, the answer is actually C. C is the correct answer. The inversion barrier for nitrogen is very low. So as I told that asymmetric hydrogenation reaction, those chiral aliphatic diamines cannot be used. So mostly what is used is the either the shock Osborne catalyst or the okay. So either it's the shock Osborne catalyst or the that carboxylic catalyst. So if you follow that, it is actually the diphosphine catalyst it is. But for the asymmetric synthesis, what it is used actually, so here they can use some olefins that quickly binds to the center it's actually cleave out when after the reaction process. So what actually happens that I am not writing this thing. So in case of asymmetric one, this type of chiral ligands are used. Okay, so mostly let's say it's one is pH and another is Ame, or this is the same. So as you can see, this is the chiral center. So as this drives the chirality into the product also. So here instead of this thing, phosphine catalyst, we cannot use the nitrogen catalyst because the inversion barrier for diamine species is around 25 kilocal per mole, and for phosphine species it is around 30 kilocal per mole. Yes, you want to say something, please? You raised your hand, so if you want to say something, you can say. Just unmute yourself and tell, or you can write it in comment box also. If not, then we can proceed to the next slide. Next question. So this is the next question that is also discussed in the section, I mean in the class. So let me check what is. Okay. So how the asymmetric hydrogenation is different from the symmetric hydrogenation. Okay. So symmetric hydrogenation means, if you say some, let's say what I actually mean there by that. So hydrogenation reaction means what? After you are taking one olefin and you are putting two hydrogens, and it basically from unsaturated one to saturated one, right? So let's say in this process you are preparing the product in such a way that it may be chiral. Okay, so let's say like if you take this so let's say you are taking this one and this one, right? So this is no substitution is there, and this is another substitution. So you can see here you don't need any selectivity after what you will prepare. I mean, after the hydrogenation, this thing will be prepared. So there is no chiral center is present, right? But in this case, what you will prepare, that this so this center is chiral center, because three type of in this carbon, three type of substituent is present. So based on whether it will be R or S, that can be synthesized from this thing. Okay, so how we will synthesize? So the chirality of the ligand plays the crucial role. Okay, depending on the chirality of the ligand, that this phosphine ligand, you will that will determine whether you will get the SR product or the S product. Okay, So asymmetric hydrogenation is this one. Okay, have we got the thing? Is it clear, right? Okay, let's go to the next one. Then. Yeah, actually the right answer is B. So in the industrial process, so what they use actually hydrocyanation reaction, and the catalyst they use that nickel cod catalyst. So hydrocyanation reaction. I mean, you know that the. I mean, let's say what is the one component of the nylon 66 is that. So this is a component, right? So to prepare these things, they actually take this type of 1,2-butadiene. So after that, what it can be done? I mean, in presence of NiCOD. So COD, cord, you know that the structure of cord that I already wrote in the previous thing. So this is the structure of cord. So this actually binds with the metal center like this one. In the same thing is in there also. So they are weakly bound to the metal center. Okay. So what happens actually before the, I mean, it comes in this way. So after the I mean, what I can say, I mean, after the before the reaction, so the ligand exchange happens. So PP3 or PPR3, it reacts, and two of this one of this cord is replaced by two of this PR3 phosphine ligand, and that makes the actual active nickel like this. Okay, so this also leave out. Okay, then actually this is actually the active catalyst for hydrocyanation reaction. Okay, so what happens is that after that these two bonds can undergo the hydrocyanation reaction, and because of that you can see that this is a long alkyl chain is there. So their most favored product will be the linear product, right, not the branch product. Instead of this thing, if you take the either the styrene or any aryl thing you take, it will give you the branched product. But mostly you will get, I mean, for these two you will get like this thing, right? So this is your product that you are looking for. And after that, what you can do is what they actually do. If you use LiAlH4, lithium aluminum hydrate, and after that if you do the acetic hydrolysis, then you will prepare this assembly diet. Okay, so this product can be prepared. And also for your information, I want to tell you that if you use the Debabrata instead of lithium aluminum hydrate, so you will prepare the aldehyde mixture. You will prepare this one. So during the which reducing agent you are using, that actually a bit tricky one. I mean that type which product you actually need. Okay, so if you need this thing, I mean for the nylon success, this is the thing we need. So after the hydrogenation reaction, they actually reduce with LiAlH4 and hydrolyze it and prepare this diet. Okay, so the right answer is this one, that you you given the correct answer. So I think there is no problem here. Then if not, then I can go to the next question. Okay, let's go to the next question. So this is also a short type question. You don't need much time to solve this thing, to answer this question. And the answer I have to yes, actually, B is the correct one. So you can understand that the in the Strock Osborne catalyst that I already told, that the actual structure is like so this is the external structure, but it is positively charged. Okay, and there is one non-conjugating coordinating anion also present as a like BF6 or BF4. Okay, so what actually it does, due to the presence of this non-coordinating anionic ligand, they actually are not coordinating to the metal center, but they are actually decreasing the electron density to the metal center. Okay, what actually it does, so it can more efficiently bind to the olefin center. Okay, so that you can understand that, right? That how much, I mean, if less electron dense will be the metal center, so it will try to pull more electron from the olefin, so the binding of this olefin and metal will be much more stronger than the other thing. Okay, so because of that, this type of non-coordinating anionic ligand were used. Okay, so answer is B is the correct one. So let's go to the second, fifth one. So it's a tricky one. Tricky one. It's doable. So we try. Actually the product you can easily actually easily can understand that what will be the product, but the mechanism is quite impressive. So that I will discuss it later. Maybe. Yes, actually it is A. So A is the right answer. So let's try to let's try to understand what is happening actually, right? So for this thing I will write it as a OR. Okay, I will write it as R. Okay, so if I write this thing, so right. So what happens actually first, that is this thing, so it can bind with the ligand, this olefin, right? So it will bind this way, and there will be OR, and there will be L2, and after the oxidative addition of hydrogen, so most probably no, this is oxidative addition will be fast, then it will be this step will be faster. Okay. So RH, this will be faster, and then it will do this thing. So if you write down the active center, actually active where the reaction is happening, active catalyst site, so this will be like this thing, and there will be 2 hydrogen will be there, and another will be this one. Right. So if you write down the actual proper stereochemistry of this thing, so you know, right, it can be like in this way. So this is the proper stereochemistry of this one. So OR is present here, ME is present here, and OR is in the upward direction. So this way OR is there, ME is there. Okay, I think you are understood. So the binding of the ligand cannot be from the upside because this huge bulky group is there. Okay, so it has to bind with the olefin through the below the plate. Okay, it is understandable, right? So whenever it will attack in this way. Okay. If it attacks in this way, so it has to first it will attack in this way, and then what is happening? Methyl is going upward. So this and this will be on the same direction. I mean, if it is in up, then you will get this product. Okay. If it is the in R, in case of R it is OH, what would happen? That same thing OH, then same thing would happen, but RH would bind from the upward direction, because in that case it could make a non-conjugative, some interaction with the OH. Okay, so because of that, the hydrogen can attack from the upward direction. Okay, so this and so if hydride can attack from the upward direction, this Me will go down. Then you will get, in this case, you will get this product. But in that case, you will get the other one, right? So this is the main difference from what. So if you want a non-directing product, then you have to make it product. If you have to protect this OH group, and if it is if you need the directed product, then you have to, then OH is okay. I think it's clear. Okay, then go to the next question. Yeah, sure.
Why this is giving precedence, why this product is giving precedence, because these both products are
No. That is what I was telling, that if you see that this is the basically difference, that whether it can happen only when the RH can bind in this upward direction, right? It is actually in the, it's olefin is up and the RH is in the down. Okay, so if it's a reverse, like RH is up and olefin is down, then only it can attack here, right? Otherwise the below attack will be the more preferred, below headed attack. And if it attacks in this way, say, then only possible way that it will make this type of bond, this type of methyl group, right? So let me draw this thing. So this thing is this. Okay, forget about everything, every other thing that are present. Okay, so if hydride is attacking in this way, so this is going upward, right? This is, and now this attack, another hydride will be in this way also. It doesn't matter because it's already one is hydride. Okay, so this thing, this is a methyl group and this is a alkyl group that add this. So this is methyl group, this is alkyl group. So this ME is always in the upward direction. You got it? What I am trying to say. But if this hydride attacks from here, then you will get that this type of thing, right? So then this hydride will be the upside, and then methyl will be the down.
Okay, sir.
You understood, right?
Yes, sir.
Okay, so that's why you are getting the this product. So but I mean, in the exam also, if you have some problem, then always try to draw this structure. Okay, you will you will have the idea why it is not in which direction it should attack. Okay, so whenever you will attack, you will draw this diagram. You will see that if the OR group is the downward side, then there is it can attack from here or here also, but it's on the upward side. So this whole portion is sterically hindered, right? So one metal center cannot, I mean, the catalyst cannot bind over here. It has to bind with the olefin through the below the plane, right? So after that, only one chance is that the hydride can attack from below the plate, and if it attacks like that, then this product is not possible. Only this product is possible. Okay. Okay. Let's go to the next question. Then you take some time to solve this thing. Afterward, I will discuss this thing. A. No, A is not the answer. The answer is actually the C. Okay, so only for this type of I mean aryl system, you will get the branched product instead of linear product. So let me draw the mechanism also. First, put another slide here. Okay, So what will happen is that if you take first, you will take this catalyst, right? So what was the catalyst? It's your This is a cobalt catalyst. First step is that ligand dissociation. Okay. So if you the CO will be out, and you will get like, right. So after the ligand dissociation, first thing it happens that the olefin coordination. So if you write down the olefin, so the structure was like this. Right. So what it will happen like, this will bind like this way, and all the thing will be same. Now the turn is that this hydrate will go into this, and that beta migratory insertion. Okay. So you can see if it is over here, I mean if the hydrate attacks over here, then the negative charge will be here, right? So this negative charge can be stabilized with because of this aromatic ring that is present over here. Okay, because of this electron withdrawing, the resonating effect. It has a resonance, electron withdrawing resonance effect is there. So it can actually stabilize the that negative charge that will be present over here. But if it is a alkyl chain, then there is not this type of stabilization is there, and in that case only possible thing is that the hydrate will attack here. Okay, so the negative charge will be here. Okay, so in this case what will happen is that you will get like this thing. So I am not writing all these things. Instead of this I am writing here. So you will find this is actually happening. Okay, after that again one ligand incorporation happens, that into the metal center, that CO binds. This is actually a concerted type of method, so there is no this is first, this is second. So after that the alpha migratory insertion happens. Okay. So when alpha migratory insertion happens, that this is actually like this. Okay. And from there, if you add the this so if you add the hydrogen, so hydrogen attacks and it actually forms that with CO, and over here this one with a little bit there is another thing, and so you will get this product. So actually what is happening here also, it is actually happening sigma bond metathesis reaction. So what is sigma bond metathesis reaction? So this is actually, if this type of thing is there, so this hydrogen bond is actually going, this force centered reaction is happening. So it basically this is actually reacting with this, and this so ligand exchange type of thing is happening. So because of that you will getting this thing, and this catalyst regenerates. Okay, so this catalyst regenerates. So always remember this, in this type of reaction, case, you also can say that the instead of this sigma mod metathesis reaction, it can do the fast oxidative addition of hydrogen, and in this case it can possible, right? It can possible that that the hydrogen will do the oxidative addition first. Okay, uh, like this way it can do that, right? This it can do like this, and after that what will do, it will do the reductive elimination and will give you the same thing, right? But it actually doesn't happen. Okay, so why it is not happen? Because you can see the in the cobalt center it is already 3 carbonyl group is present, and actually the other carbonyls are also present, that 4 carbonyl group is present. So it is already very electron deficient type of ligand. Okay, the metal center is already very electron deficient. So further hydride incorporation means further it will, the electron density will decrease further. So that is not actually a quite I mean quite a stable thing. Okay, so rather than that, it will do the sigma bond metathesis reaction. Okay, so but always remember that it is, if the oxidative addition and reductive elimination is favored, then it will sigma bond metathesis reaction will not happen. Sigma bond metathesis reaction only happens when this oxidative addition and reductive elimination is hindered or non-favorable or highly energy demanding process. Then only this sigma bond metathesis reaction will take place. Okay, and you can see that the sigma bond metathesis reaction, if we add all this oxidative addition and reactive elimination, you will get the sigma bond metathesis reaction, right? Because the same thing is happening. If you merge those two steps, then you will get the sigma bond metathesis reaction. I mean, the process is similar. Is it you have any doubt over here? If not, then we can go to the next step, next question. Okay, let's go to the next question. So it is actually hydroformylation reaction. So it is the hydroformylation reaction that I told you. This is also an easy one. I mean, you can try. I mean, No, it's not C. The answer will be A. Sorry. The answer will be B. Okay. So both are actually a false statement. Okay. So if you why one is not true, because you can see that the Strock Osborne catalyst, that is actually the that I already wrote down before also, that right. So they are one weekly binded olefin is binded there. So this is actually not a drawback. Okay, the catalyst were designed in such a way that if there will be a this weekly binded olefin will be present. Okay, so why it is that if you don't put this olefin over there, it can do other type of reaction. Okay, so to stop that reaction, this type of weakly conjugated olefins were used to the metal center, and it also directs the actual olefin that we want to do the hydrogenation reaction, that will actually binds on that place. Okay, it leaves that place, and the other olefin that is needed to do the hydrogenation reaction, that actually binds over there. Okay, so it actually directs the that olefin to bind in that place. Okay, that's why it's not actually a drawback. It the catalyst designed in that way. Okay, and the second statement is hydrogenation catalyst cannot be used for synthesizing artificial amino acid. That is actually very wrong. Okay, so I already told you in the first question where I discussed that which one is the Strock or Osborne catalyst, which one is the Cartry catalyst, which one is the Wilkinson catalyst. So all of these three are the dihydrate catalyst, but mostly they are used that Osborne catalyst and the Strock Osborne catalyst, or the Cartry catalyst. They are mostly used to synthesize this artificial amino acid. So as you know that the most of the artificial amino acid, natural amino acid we have in our body is mostly the L amino acid. Okay, not mostly. I mean, it's very rare. It's you will get any D amino acid or anything. Okay, mostly it is L amino acid. So how we will prepare the D amino acid then, and other variant of the amino acid? You can use this. Okay, you can use this is the basic uh, structure of amino acid, right? I am not I mean drawing the stereochemistry of this thing. So this is the basic structure, right? So if you vary this R group, then you will get a different type of thing. Okay, let's say you write in this way also. That will be easier for you to understand, right? So instead of that, if you do the retrosynthesis or all those things, so you understand that if you take this thing. Okay, so you can get either the D product or L product, right? So from there, the L is already naturally occurring. Okay, so the D one you can get it from the artificial way. So if you do the hydrogenation reaction over here, you will get either D or L. So for this thing, this type of dihydrate hydrogenation catalyst are used. Okay, obviously you have to take the protected one over here. Protected, you have to protect this amino acid and all these things you have to do. But you can get the stereoselective product of the through this process. Okay, so it's actually so this statement is also false that Dihydrogenation catalyst cannot be used for synthesizing the amino acid, artificial amino acid. Okay, so both the A and B, I mean the statement 1 and statement 2, both are actually the wrong statement. Uh, you got it or not? I mean, if you have any doubt or query, you can write it in the chat box, or you can uh, ask me also. If not, then we can go to the next question. Okay, so good. So yeah, P is the right answer. So let's try to actually understand the what is the mechanism of this thing. So okay, this is actually a Wilkinson catalyst, right? So what is happening is that as you can understand that first step is that the ligand dissociation, right? So it will form like this way, and after that hydrogen will bind to the metal center. So this is the oxidative addition reaction. So let me redraw this thing. It would be good if we write it like that. Okay. After that, that olefin coordination. So one, two, three, four, five. So it can be this type of thing. Okay. So what can happen that this it will be if the olefin binds with the metal center. So this is the thing that can happen, and as I already told you that this is the alkyl type of thing, right? So the beta hydride beta migratory insertion will be always the linear one, right? So I am showing this thing, but during the beta migratory insertion, that I already told that when the bit, that means what? If it is this metal center is binding, this is alpha, this will be beta. When if the metal center bind over here, but it is actually a electron as you have understood that from the when I talked about the branching and the linear product. So you can see that this is mostly the what I will say negatively charged thing, right? This there is, it can act as a nucleophile over here. So what it will do, it will react with the this carbonyl center, and because of that this will go out and you will regenerate this catalyst. Okay, and instead of that you will get what? You will get this product. Okay, so you can say that the how it is actually happening and all this thing, but it is not in that simple type of thing. Okay, if you write over here this is the beauty of this organometallic type catalyst. Okay, so it is not actually a straightforward that nucleophile is attacking over here and it is doing all these things. Okay, so what it can do, I am not writing other parts. So it can actually bind over here, right? So this is the 5 center ring that is actually preparing. That is actually prepared. So this actually hydrogen is very much is in affinity towards the towards this metal center. So that's why it can attack over here, and this can actually bind over the ruthenium metal, and because of that this is getting produced and it will go into this stream. You understood? If you have any confusion you can ask.
Yes, sir. Sir, I think you have given the answer of my question. But sir, I just want to ask you that,
Okay.
sir, I often confused while doing the reaction mechanism that what we should look like means we have to see the substrate and organometallic catalyst both, or we can just predict the uh, reaction pathway by the organometallic catalyst that we are using. So it means why in the first step you done the PPS ligand dissociation.
Okay, I mean you understand that all of this whatever reaction what we are telling you. I mean this is not actually we explained in other way. Okay, so you do a reaction, you obviously you have some idea what can happen, or all those things. You do the reaction, you get a product, and on that basis we actually give the this plausible mechanism. And sometimes it happens that the all these intermediates can be determined in various spectroscopic method, and you cannot in many cases it happens that the you those intermediates is not, you cannot explain, I mean observe, you cannot observe with the spectroscopic method. Okay, but you have to give the explanation in such a way that the that is actually that will be a logical way, logical thing. Okay, if the logic is correct, then everyone will think that it may be the one type of mechanism that is actually happening. Okay, and all this mechanism whatever is there is mostly this basic type of reaction that we talked about in the previous session also, that either you will get oxidative addition, reductive elimination, ligand dissociation, beta migratory insertion, alpha migratory insertion, the beta elimination, alpha elimination, all those things. I mean তারপর sigma bond metasis reaction, all these reactions are the basic reaction, and on that basis we are preparing this mechanism. Okay, that this catalytic cycle. So and you right, you asked me why pp3 is dissociating like that, right? So if you do the electron count, you will you will get the answer. Okay, so if you do the electron count, then you will either find not in this case, I mean you will find either it is actually a either it is 18 electron species, then you cannot do the oxidative addition reaction, right? So then you have to go back to the 16 electron species. The way how you get the 16 electron species, you have to have a ligand dissociation. Then only you can get a 16 electron species, and then can do the oxidative addition reaction. Okay, so in that way it works. Okay, it's not like that it's have, I mean it can be done in any way. Okay, so you can not do this ligand dissociation after two or three third step. Okay, everything has a logic, but you have to understand why it is why we are using it in using that. Okay, why we are using that logic. But it is also true that it is not that the we first predict the mechanism. Okay, we get the product, and after that on the basis of that product we give the I mean we give the mechanism. Okay, I think got the answer. Okay, let's go to the next question. Okay, no, the actually answered wrong statement is actually the uh, Wilkinson catalyst is based for tri or tetrasubstituted olefin. That is a wrong statement. Okay, I already told you that the Wilkinson catalyst is only suitable for the mono or disubstituted one. Okay, if it is tetra, not also disubstituted one, monosubstituted one. So if it is a tetra or tri, the best hydrogenation catalyst is actually the Stock Osborne catalyst or the Cartry catalyst. Okay, so this is actually the wrong statement. Okay, you understood? And asymmetric thing, I already told that asymmetric hydrogenation is possible when the chiral phosphine ligand is present. Okay, and a crystallized intermediate from a reaction mixture may be an off-cycle intermediate. Yes, I mean it is maybe off-cycle intermediate means that is a part of the catalytic cycle. Okay, you are getting a crystallized intermediate. That means the abundance of that intermediate into the solution is much more higher. Okay, so you, in the process you understood that the I mean if it is in this cycle, if it is any intermediate is there, say already all these intermediates are actually is uh, is, is in the cycle, right? So it is consuming and then it's also producing. So it will not crystallize in that way. If it is crystallizing means that the it is a off cycle intermediate. That means it's not a part of the cycle. Okay, it can be a product also, I mean, if possible. You understood? Okay, let's go to the last question. So I will not go to the mechanism I mean, of this reaction, but you can try it in your home. If you can't, you can mail me or mail me. I will try to explain it. But it is your I am keeping it your homework because you have some doubt regarding this catalytic cycle. So you try to solve it, okay? But I will give you the answer, and you also understand why I am giving this. Oh, I will give you the answer. I mean uh, the product from the product you can understand that which type of reaction it is. Okay, so from there you can predict the reagents. Okay, reagents and the catalyst. You see that forget about this ring. Okay, so this is actually maybe the maybe na this is actually after the some addition reaction during the last step. This is actually here this is forming something and it will react and this will go out. Okay, and afterwards it will hydrolyze and it will form this double bond. That is the other thing, you don't need to bother about that thing. But you see what is happening here. Okay, CO2 so how you can get CO2? Okay, so if it is the hydrogenation reaction in the olefin, you will get that the olefin the olefin uh, uh, will do the reaction with the hydrogen, and from unsaturated one it will be saturated one, right? So that is a hydrogenation reaction. And hydroformylation reaction, what is it? It is so you are preparing the carbonyl group over from the aldehyde from the olefin, right? So that is a hydroformylation reaction. Here, what you are getting? You are getting COM, carboxylate type of thing. Okay. So what reaction it is? It is actually a hydrocarboxylation reaction, right? So otherwise you will not get the those things, right? So if it is a hydrocarboxylation reaction, and other one, whatever what you have studied, that was the hydrocyanation reaction. So in that case also the same thing. So that CN cyano group is getting inserted into the olefin center. Okay, so one thing that from there you can predict that this is the carboxylate group. So the carboxylate group is producing from the olefin, so it is a hydrocarboxylation reaction, carbonylation reaction. Okay, so if it is a hydrocarbonylation reaction, then a carboxylation reaction, then what is the process of that? You need the one carbonyl group, that is, this is this one, right? So what is coming from? You need one carbon monoxide, that is this thing, and you need for the OMe, you need something, that is the methanol, and you know for the hydrocarboxylation or the hydroformylation reaction, this catalyst is used. I mean, this very straightforward thing. You, if you don't understand those catalytic cycle, it's also fine. You logically try to understand this thing. Okay, so for hydro genation reaction, those catalysts are there, Wilkinson. Okay, then Cartry and other this what Stock Osborne catalyst. Okay, for the hydro or relation case, what is happening? This is needed as a catalyst, and for the hydroformylation, hydro sorry, you need nickel catalyst. Okay, it's clear, right? So here, what you need, it what I told you, it is a hydrocarboxylation reaction. So you need one thing, that is the catalyst you need. This is the this is your this cobalt catalyst. Okay, so this is the thing that you need for this reaction. In the catalyst cycle, you try to solve it in our own. And I already, in the previous day, I already provide you my email number. If you cannot do it, you can reach me over mail. Okay. Okay. Then so this is the end of the class, end of the session. If you are giving the exam, I will wish you. I'm wishing you best of luck for the exam also, and study hard from those those basic from those basic things the question will be asked. I think, I don't know what they will ask in the question, but those will be the basic one. Okay, so you can follow those video lectures, and also you can follow the for some good there is so many good organometallic books are also there. Okay, so for books that I am telling you, that you can read the BD Gupta. Okay, BD Gupta is actually a very good book. I also in my masters, I also read that book. From there, I have got a few knowledge on organometallic. So that is actually a decent book, okay, that you can that you can read. Okay, this is very in easy, very easy way. It was everything was written there. Okay, if you follow, I mean, you don't need to I mean, you need to study all these things, but some basic things are there that you need to understand from the from organometallics topic. So one thing is that electron count, 18 electron, 16 electron, those pieces you have to that count, you have to do it. And that metal bonding, in that way you will get that the when the you will do the electron count, you will get whether there is metal bonding is present or not. All these things is comes there. And then backbiting, back not backbiting, back bonding. And then carbon is there. Carbon is a very big a big topic over the in the organometallics code the topic. So that is not discussed in this lecture, but carbon is a very important one. Okay, so whether there is two type of carbon is there, there's soft carbon is there and another carbon is also there. So those you have to, yeah, I actually don't have that much time. If I had that time, I would uh, uh, see, I mean, it's very difficult for me to show you what I do actually. Uh, Not a very big thing I do. I mean, you better. I mean, it's very common. I mean, you if you will go to the PhD, I mean, you will find the most of the lab does the same thing. So, but I don't know in which class or in which I mean, you are in master degree or PSc. So you study all these things. Your focus is now should be learning, not in the lab thing. You will get the opportunity later. Okay. uh, so what I am telling that you should learn the read the carbon section. And then was this catalytic cycles, catalytic this reactions, basic reaction. And another in I mean, actual thing is there, that is the coupling reaction. That is also a very crucial one that was not covered in here. Okay, for the knowledge purpose, if you want to study this organometallics thing, you borrow one PD Gupta, you will get any library or anywhere. So PD Gupta is a very well known book. So the name of the book may be the Introduction to Organometallics. Okay, so I forgot the name, but most probably the name is the Introduction to Introduction to Organometallics. Okay, so the writer is BD Gupta. BD Gupta, and another writer is also there. I forgot his name. So whatever it is. So okay, this was the last session. So okay, then if not, then I'm stopping the recording. And maybe if I take any other class in future, I mean, then we'll meet. Yeah, and if you enroll in that course, we will meet. Okay.